Welcome. The title of today's lesson is Describing Location in a Distribution. We have spent some time trying to find mathematical ways to represent a data distribution. Now what we're going to do is take a particular value and describe its location in that distribution. So the first way we're going to take a look at it is what is called percentiles. And so let's just jot a few things down and do an example or two with it as well. So we're going to look at what we would call the pth percentile. P with a little th there. So that percentile of a distribution is the value with p% of the observations less than it. Okay, so jot that down, and obviously we'll do an example or two to kind of back that up. So again, it's the location of a particular value in the overall data distribution. And the one way to talk about it that we'll start out with is what is called the percentile. All right, so example one. Every year the math department runs a March Madness. For those who don't know, March Madness is a men's college basketball pool. And so we did this last year, and the following data set shows the scores of the 18 contestants. So my score, again, a particular value, my score is right here in bold, the 190, and just determine the percentile. What would be the percentile of my 190? And so, again, really not too bad. What we want to do is take the number of observations less than the 190. So again, if we want p% of the observations less than that, so let's think about this quantitatively for just a second. How many of the scores were less than 190? So here I am. I came in 4th place, by the way, not too great. But out of the 18 contestants, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 contestants finished lower than I did. So I did better than 14 of the 18 contestants. So if you're not sure, this is the number of contestants with scores less than 190. And then what we want to do is take that and divide by the number of contestants total. And in this case, there were 18, the total number of observations. So this is how many were below my score. This is how many scores total. And if you do this, let's go ahead and actually get that calculation just to make sure. So I'll bring that on up, and obviously just going from fraction to decimal to percent, not a big deal. So 14 over 18 is this, so about 77.78%, somewhere in there. Typically, we're going to go to the whole percentage. And so if we want to know what percent were below me, I don't want to round up. I don't want to say 78% because not necessarily 78. So we're going to round down. So I would be in the 77th percentile. And so just round down to the nearest whole, if you would. I've seen it many ways. I've seen it rounded, but mostly I've seen it rounded. So that looks good right there, to the nearest percentage. So I would be in the 77th percentile in that particular pool. Again, calculation really not too bad. All right, so it just so happened my daughter entered this pool as well, and she doesn't know anything about college basketball. And so she just kind of picked teams, and she was the one that got 96. At least she didn't come in last place. Good for her. Well, anyway, what would be her percentile? And so in this case, again, 18 total. Not too bad, again. 18 down there. And what we're looking for is the number of observations that are less than hers. So she was the 96, and there are only 2 observations less than her. So 2 out of 18. And again, same deal. We would just take that and represent it as a decimal then percent. So 2 divided by 18, and we get 0.11 and change. So rounding to the nearest percentage, she would be in the 11th percentile. Okay, poor Leah. All right, very good. So again, just number of observations below our particular value and over the number of observations total. and that would be the percentile, and that would be a way to sort of determine or describe the location in a particular distribution. All right, hope that makes pretty good sense so far. Now what we're going to do is take a look at it from just a slightly different perspective. As it says, so let's look at the position of Mr. Meyer's score from a different perspective. Where does his score of 190 fall relative to the mean? So determine the mean and standard deviation of the data, then draw a conclusion. Okay, very nice. So we can do this a couple different ways. You can enter the data on the calculator and go to that one variable stat. I'm not going to go ahead and do that at this stage. But remember, you go to stat and move it over to calc, and there's the one var stats on it. Or you can just add them all up and divide by, in this case, 18. And that, I think, is what I did in this case. Although we have to get the standard deviation, so I guess we do want to put that in. Sorry, change of mind there. So let's go for it. Let's put it in. Good practice for us regardless. And we're going to need to get it this way from the standard deviation as opposed to using the formula. So, all right, here's what I have. So let's put in the data set. And I'll try to be fast with this. I'm sure you're going to be done before me. So enter your data in. By now you should be an expert at that. Okay, my score at the 190, not good enough though. Okay, there are your 18. Look good. Let's go ahead and turn the stat plot one on. Just get that going. So just go to the y equals there, turn that on. Looks good. Once that stat plot is on and it's ready to go, go over to stat and calc. Let's get that one variable stat on this. And there we go. Looking pretty good. So a couple pieces from here that we can steal. Remember the 5-number summary is kind of below here, but there's your X bar right there. We'll write that in. And here is your standard deviation right there as well. Okay, not too bad. So it says determine the mean and standard deviation, then draw a conclusion. So obviously, let's get those pieces going. Here's what I have. First of all, X bar is going to be about 159.72. So the average of all of those scores. Now remember what the standard deviation represents, of course, the average distance of each value from the mean. And so the average distance from the mean is about 44.9. And again, I'm going to write that below. It's always good. Standard deviation, average distance from the mean of those values. Okay. So let's talk about just those two, and then let's use my value, the 190. It says, where does my score of 190 fall relative to the mean? Well, obviously, it's above the mean. And here's what I have on my paper. It seems if we do the calculation, it is about 30.28 units above the mean, right? Is everyone okay with that piece? That's how far it is above the mean. In terms of compared to the standard deviation, is it a full standard deviation above the mean? No, because this is only 30 units above the mean, where the average distance is 44.9 units above the mean. So is everyone okay with me saying it's maybe about 2/3 of a standard deviation above the mean? Does that phrasing work for you? So again, this is how far my score was above the mean. On average, the individual values are 44.9 units away from the mean. So I would be about 30 over this, so about 2/3, give or take. Don't know if I did that decimal what it would be, but we'll figure that out, I'm sure. So it's about 2/3 of a standard deviation above the mean. And remember, when we talk about the mean, what we really mean is sort of a typical score. So remember, mean is the center, a way to describe a typical value in the distribution. So the mean, a typical score in this case. So I was about 2/3 of a standard deviation above what we would call the typical score in the distribution. All right, not too bad, right? Okay, so this is exactly what we're going to do. We're going to measure the position by standardizing our values. And when we do this, it is what is called a z-score. We're going to talk a lot about z-scores here over the next several days. And so the z-score very simply comes down to this. If x is an observation from a distribution with a known, and this is what we got before, mean and standard deviation, then very simply, the standardized, again, we'll talk about that word quite a bit over the next few days, the standardized value of x is, and then as you can see on your paper, there's a nice little formula to get us thinking about it. And here's pretty much what I did to come up with my z-score, and we'll do this a little more formally in just a second. I did it more of an estimate in the investigation, but to get our z-score, we take our individual observation, subtract the mean, that's what I did, subtracted the mean, and then divided by the standard deviation. And so I thought about it in terms of how comparing this to this, it's about 2/3 of the way to that first standard deviation. Okay, good. And that's exactly what we're going to start to work with, our z-scores. It's comparing it to the mean and the standard deviation. Okay, perfect. So it says, determine the z-score for Mr. Meyer and his daughter, so we'll do it 2 times over. Again, easy calculation, not too bad. And then we'll do the example 4 right on below it here. So the z-score for me, a standardized score, my score was 190. What we're looking for is, what is that score relative to the mean? And in this case, let's take away the 159.72. And of course, divide by the standard deviation, which we got is about 44.9. And so this would give me my z-score. And watch the number we get here, and we'll see how my estimate was when I did this before, just thinking about it logically. So let me just quit this right here and clear that out. So 190, do it with me if you would, minus 159.72, get that, and we divide by the 44.9, and notice what we get. I said it was about 2/3 of a way towards that first standard deviation. Do you see, 2/3 is 0.6 repeating? And I was pretty close, all things considered. So the z-score is about 0.67. And so what we would say is my score was about 0.67 standard deviations above the mean. Is that okay? Comparing it to the mean and standard deviation, that's what we would say. Not quite 1 full standard deviation above the mean, about 0.67 standard deviations above the mean. All right, how about poor little Leah here? So her score was the 96. So let's see her z-score, and again, related to the standard deviation and the mean here. So 159.72, divide by the standard deviation, 44.9. So let's get her z-score and think about how we would reference it and how we might describe it. All right, I'll go ahead and bring this up as well. Let's see what we have going. So let's take 96, take away the 159.72. Great, and now divide by the mean, the standard deviation, 44.9, my bad, and we get that right there, about negative 1.42, give or take. So her score, a standardized score, was negative 1.42. And essentially what that means is she was about 1.42 standard deviations below the mean. Hope everybody at this stage is starting to see what it means to have a standardized score. It's in relation to the mean and its standard deviation, and this is how we would phrase it. 1.42 standard deviations below that mean. All right, very cool. Let's do one more here. We've got some time to pull off example 4 before hitting the back side. So little Timmy took 2 tests on the same day. On the first test, he received an 86. The teacher mentioned that the mean score was 80% and standard deviation was 6. Second test, he received an 82%, so not quite as good just in terms of raw score. That teacher stated, though, that the mean score was 76% and the standard deviation was 4. Describe little Timmy's success on each test compared to his peers. All right, perfect. So as we kind of look at this, again, we talked about, well, we opened this notes worksheet talking about percentiles, and now a way to measure one value in relation to the others is by using the z-score. So let's do it for the first test and then do it for the second test. And again, calculations really shouldn't be too bad. So if I remember correctly, first test was an 86, and the mean was 80. So in relation to the others, based on the mean and standard deviation, and standard deviation for this one was 6. So the z-score, really not too bad. 86 minus 80 is 6. 6 divided by 6. So this one, z-score exactly 1. So 1 standard deviation above the mean. That was his standardized score. 1 standard deviation above that mean. Perfect. Now the second test, again, the raw score was lower. Should he feel worse about that score or better when he compares himself to the entire class? So in this case, got an 82. Mean score was a 76. And standard deviation, so the variability was smaller in this class compared to this class. Standard deviation here was only 4. And so when we go ahead and do this, 82 minus 76 is 6. 6 divided by 4 would be 1.5. So in terms of his success compared to his peers, he was 1.5 standard deviations above the mean on this test. So in terms of relating it to his peers, looks like better on this test than this test over here. All right, so we have our standardized score to talk about the location in a distribution. That looks great. Let's move on. So let's see what we have going here, and actually not too much on the backside. We'll build on these ideas in the next couple lessons, but not much we can do with them at this stage. So it says on your paper, thus far we've explored quantitative data both visually. We've done some dot plots, some histograms, box plots, etc., and numerically. Obviously, the primary measurements with data sets have been through the center, mean and median, and the spread, standard deviation, and IQR of the distribution. We're going to take it one step further by overlaying a smooth curve over the distribution, and this is what is called it says it on your sheet already. That's all right though, a density curve. And so you can see I've got this histogram right here, and a density curve would just be a smooth curve overlaying the visual representation right there. Okay, a couple characteristics of a density curve that we need to be careful of, and so let's get those pieces in play. So first of all, a density curve is a curve that is on or above the horizontal axis. So you see this curve right here, all of it is above the x-axis or the horizontal axis that we have in play right there. And you can see a couple of the other ones down below as well. So on or above the horizontal axis, and here to me is the key. It has an area of exactly 1. So the area under every density curve is exactly 1, and that is in order to represent 100% underneath it. So the 1 represents essentially the 100%, the entire proportion underneath it. Okay, good? And we'll get into that in just a little more detail. And very simply, a density curve in just basic terms, it is a description, a visual description of the overall pattern. So it describes the overall pattern of the distribution. Now we're going to be taking a look at a very particular type of distribution and density curve in the next couple lessons. So this is really just a prerequisite to that. Okay, again, not really too much more to do on this particular notes worksheet, so let's just put a couple things in place here just so you can see it visually, and then we'll go from there. So it says, in addition, the area under the curve and above any interval of values on the horizontal axis is the proportion of all observations that fall in that interval. So this is exactly what we're going to focus in on in the next couple lessons. So first of all, take a look. By definition, the total area under the density curve is equal to 1. So if I look at all of the observations are underneath this, and as a result, 100%, or the area being a value of 1. And so when we focus on a particular interval, and this is obviously fairly arbitrary at this point, when we focus on a particular interval, this is the proportion of observations in this interval. And it's in relation to the 100% or 1. So we would say here, if this area is 0.12, then, and this is the only thing I'll pretty much write the rest of the way, is, that's a poor 12. Let's do that again for you. So that 0.12 means that 12% of the observations are in that shaded interval. Okay, so I hope that makes sense in reference to the overall density curve. The shaded area right here would represent 12% of the entire area. And so what we would say is 12% of the observations, fall in this interval. Okay, great. And then maybe just one last thing to quickly refer to and then go from there. We had actually talked about this before. We looked at it I think in a little more numerical terms, but I think this works out fine visually. It says the mean and median of symmetric and skewed density curves. So remember, in this particular case, if it's symmetric in nature, and we're going to take a look at this one in particular in the next couple lessons, this is maybe what the density curve would look like. And you can see that the mean and median are basically the same. And in fact, we kind of wrote that down, comparing mean and median based on the distribution. And we said symmetric, typically mean and median are very close together. The more symmetric, the closer together they are. So the way it works out, actually, if it's perfectly symmetric, they're the same. So I'm just going to write that. So same for symmetric density curve. And for a skewed one, do you remember we kind of talked about this? The mean is further along the tail of a skewed distribution. So if this is right skewed, then the mean is going to be the right to the right of the median. And that's exactly what we have here. So we kind of looked at this numerically. We actually wrote this conclusion down on a previous notes worksheet. But if we had a density curve that looked like this for a right skewed distribution, the mean is further along the tail, further along the skew. So I'm going to go ahead and just write that piece here, and we'll wrap this on up. So the mean of a skewed curve is pulled away from the median, really in the direction of the tail, the way it is skewed, of course. again, I think we had already developed that conclusion. Just good to kind of take a look at with these density curves and see it more visually. All right, great. I think we'll leave it at that. Again, we're going to look at a very particular type of distribution coming up in the next couple lessons here. And those z-scores are going to come up. So good lesson here, a good sort of a segue lesson between the last two and the next two notes worksheets. Hey, thanks for listening, everybody. Let me know if you have any questions.